There are a number of standards to calculate the short circuits in electrical network. Today I will discuss the IEC 60909 standard and see how to implement a short circuit calculation using this Python software. For instance, we have a grid or electrical network extremely simplified. We have a grid, as you see to the left of the schematic, and two bus bars are connected with a cable and an overhead line. And the target of this tutorial is to calculate at fault location F the short circuit current applying this IEC 60909 standard. The parameters given for grid and other cables and overhead lines are listed here. The short circuit current for the grid is 31.5 kiloamperes, and for this particular case the ratio of resistance to reactance is given to be 0.1. For the cable used, the resistance per kilometer is given as 0.08 ohms and reactance is given as to be 0.14 ohm per kilometer. The total length of the cable is 50 kilometers, and similar parameters are given for the overhead line. The length is 35 kilometers. According to the standard IEC 60909, if the resistance of the grid RQ is unknown, the following empirical formulas are typically used as listed here. But there is also a second case in which we also have the ratio of resistance to reactance, which is the case for us. We can first calculate the XQ, the reactance of the grid, once we find ZQ, of course, and then from that ratio we can calculate R and Q. I will import, for example, to calculate the short circuit currents and impedances, a package from Python called NumPy. Let's import NumPy as np. Let's run it. And since we saw that we have the short circuit current is given, in that case we have this relation to calculate ZQ and XQ. Let's write the given parameters first. We said IQ Q, for example, is equal to 31.5 kiloamperes. What we have, U and Q is the voltage of the grid. I'll write this smaller Q. It should be 110 kilovolts. Rx, I will just write Rx, that is the R by X actually, the ratio, it's 0.1. If this is the case, I will also take a factor C, maximum to be 1.1 for the grid. And if this is the case, let's first implement this equation. That means the second part of ZQ calculation, which is C times U divided by square root of 3 multiplied by the short circuit current. This is what we are going to implement. That means if we write ZQ is equal to, I will take C multiplied by U and Q, as a C times voltage, divided by square root of 3 times, we should have the current IKQ. This should give us the impedance. Now this impedance is the magnitude of the impedance. Let's continue. Since we now know the ZQ, we can now use the second relationship to calculate the reactance. That means XQ is equal to ZQ divided by what we have, square root of 1 plus r by x, and that is for all case rx and square, rx square. And if we want to calculate the complex impedance, we can just write zq, or let me call it z grid, and that's to be, is it the complex, the function? Yes, complex, rq. Okay, I didn't calculate rq, which can be calculated from the ratio rx, which is r by x, and multiplied by xq here. And if we have rq and xq, we can construct the complex form r plus jq. To write it in Python, it is rq comma then xq. So let me run it. To show the complex integrand, I will just print that grid. Let's see. So here you can see the complex impedance. The first part is the resistance, and the second part is the impedance of the grid. Now let's not forget the target is to calculate the short circuit current at this point F. For that, we need, once the impedance from the grid, the parallel connection of the impedances of cable and overhead line, and then we can calculate the short circuit current at point F. So the impedances of the grid we just calculated. The same we need to do for cable and overhead line impedances. That means we have here the per length ohm of the cable and overhead line. So we can just multiply them to calculate the total impedance. So let's define the length of cable 35, and then we have, let's say, the per unit impedance RC prime is equal to 0.08. This is the ohm per kilometer, so to speak. And if we want to have the reactance, that is R prime is equal to 0.14. If we want to calculate the resistance of the cable, RC, then it is simply RC prime multiplied by its length. And same for XC, which is XC prime, enter, times LC. The same calculation we can do for the overhead line. I completed it already. Let me just copy and paste the code here. I think this is the best variant. We have this. For example, we have the overhead line. I think I wrote it wrong, but since I have the consistent values, then it's not a problem. It should be OHL. Anyway, it's done working. So this way we just calculated in these two lines the impedance of the cable, and in these two lines the impedance of the overhead line. We can calculate the complex impedance of the overhead line as well if we needed to, but I'll leave it as it is now. The next step is to calculate the equivalent impedance up to the point F. That means we need to consider the grid impedances, the parallel connection of these two impedances, and then we can finally calculate the short circuit current at point F. For the total impedance, or the equivalent, it is simply the equivalent. So that means ZK is the impedance at the fault location, is this Z grid in terms of complex impedance plus the parallel connection of cable and overhead line. And if we separate or extract the real and imaginary parts of the impedance, it is RK and ZK. In terms of magnitude and phi, just for a quick check, we have these values. Let's run this cell as well. Control Enter. It's okay. If we want to see the values, for example, here, just print ZK mag, and for the angle value, it's also convenient for me to check. It's print, not print, and print ZK phi. If I have this value, let me quick cross check if the values are correct. I also solved this problem by hand, so I'm quick checking. 6.57, 69 degrees. Okay. And now is the step to calculate the symmetrical RMS short circuit current at point F, because we calculated also the equivalent impedance up to the point F. So in order to calculate the three-phase symmetrical short circuit current IK double prime, we have CEN divided by square root of 3ZK. Now we can write this again, the token of code. The voltage at bus bar A and B is for both is 110 kilovolts. IK double prime, that means I am implementing this equation here, is C multiplied by EN divided by square root of 3 and magnitude of the impedance. And since I wish to get the current values in kiloamperes, I divide it by 1000. And let's show the value of the current value here. It's now 10.619 kiloamperes. So this is the symmetrical initial short circuit current, and if we would like to calculate the peak value of the initial short circuit current, and with the assumption that is the uniformly distributed ratio of R to X, then we can use this formula, which is IP is equal to kappa times square root of 2 and IK double prime. Now the factor kappa is then again calculated with this relation. It depends on the ratio of the resistance to reactance to that fault location. To calculate it again, let's define the variables first, or initialize them. RK, XK, I will call them as the ratio of RK, XK, or RK divided by XK. If you remember, we had extracted the values RK and XK already, and then kappa is simply the implementation of this relation here, and IP is equal to kappa times square root of 2 times IK double prime. Let's check the values. So we see the initial peak short circuit current is then 20 kiloamperes, which was 10 kiloamperes, or 10.62 kiloamperes in terms of symmetrical RMS short circuit current. So this is quite a basic circuit to calculate the short circuit for, but if we have a much more complex circuit, the application of the standard IEC 60909 would be similar. In the future videos, we'll see how to calculate for much more complex electrical circuits, including transformers or other electrical equipments, cables, grids, and for complex and at also different bus bars as well. So in that case, calculations could be also quite complex, and in future videos we will just check them with computer supported simulation programs like Power Factory. Until then, thank you.